Okay, welcome back. So last time we gave one result of Lyapunov's, which was actually kind of, I said, a footnote in his work, which was about what can you say about a nonlinear system stability around a particular equilibrium point based on its linearization around this point. And if the answer had been nothing whatsoever, it would have been rather scary. But the answer was basically if the linearization is strictly stable, then locally the stability of this point is asymptotic, although it doesn't tell you what locally means. Okay, it says there exists some region such that the stability is asymptotic. If the linearization is unstable, then not surprisingly, the nonlinear system around this equilibrium is unstable, meaning not stable in the sense of Lyapunov. There exists a ball such, however small the small ball around the equilibrium point, you will always find a trajectory that escapes from the big ball, right? And then there was the case of marginal stability if the linearized system was marginally stable around this equilibrium point, then actually you didn't know at all. Okay? And the reason you didn't know at all was that basically when you linearize the system and the linearization is marginally stable, you've thrown away the important information about stability by throwing away the higher order terms. Okay? So when the linearization is marginally stable, it means that's not where the action is. Okay? The action is on the higher order terms, and so basically if you just look at the linearization, you've thrown the baby with the bathwater. Okay. So that was the story. Then we discussed how we started discussing the main result of Lyapunov, and there's lots of versions of it, but the main result of Lyapunov about stability around an equilibrium point, and we started proving this. Okay, so remember the theorem on local stability which is theorem 3.2 for those who have the textbook. So it says, consider some ball, BR0, and assume you can find a scalar function v of x. And remember, we made this remark last time that while we were talking about autonomous systems, x dot equal f of x, around a particular equilibrium point, 0 without loss of generality. The reason we were talking first about autonomous systems and then about more general, possibly non-autonomous systems, was that if you have an autonomous system, then d over dt of v of x is dv over dx times dx over dt, and dx over dt is f of x. So this whole quantity, d over dt, could be written, as we said last time, as v dot of x. Okay? So if you have an autonomous system, if I give you v of x, and of course I give you the dynamics f of x, then you can compute v dot of x. Okay? V dot does not depend on time explicitly. So if you have a scalar function v of x such that v of x is positive definite in that region, of course, BR0 in this ball of center 0 and radius R0. Okay? So such that v of x is positive definite in that region, and v dot of x is negative semi-definite. So remember, positive definite meant it was 0 at 0 and strictly positive everywhere else. Okay? Negative semi-definite just means it's negative or 0 everywhere in that region. Okay? So if you had this, then this equilibrium point, I wrote it more explicitly last time that this equilibrium point s equals 0 was stable. Okay, so if you have these two conditions, v positive definite, v dot negative semi-definite, then the equilibrium point is stable. If more precisely, you still have, of course, v positive definite, but v dot is negative definite, okay, then this equilibrium point is asymptotically stable. Okay, so that was the theorem, and we had started proving this. Okay, so remember how the proof went, right? We said if we pick an arbitrary r, we want to find an R0 such that whenever we start, sorry, not an R0, a small r, sorry, such that whenever we start in this ball of radius small r, we never get out of the big ball. Okay. And so the idea of the first part of the proof, proving this, was very simple, but very astute at the same time. It was saying, okay, so you have this arbitrary ball of radius r. Let m be the minimum of v of x on the sphere, in other words, the shell of this ball, x equal r. Okay. Then I can construct, I won't redo the whole proof again, right? I can construct this ball here of radius small r such that the value of v of x in this ball is always less than m, right? Because the value is 0 and v is continuous. So the value of s is always less than m. And in addition, I know that v dot is negative, so v can only decrease. So if I start with a value always less than m, the value of v will remain less than m, and therefore it cannot possibly cross out of the big ball, because on the big ball the minimum value is m. Okay? So very simple proof, okay, which we stated last time, right? So you have r, you compute the minimum. This allows you, at least numerically, to explicitly compute small r, okay, the best small r, okay, such that whenever you get in this ball of radius small r, you never get out of the big ball, okay? And that proves stability, okay? Any questions about that? Okay. And again, you know, feel free to interrupt with questions. If you haven't understood, it's likely half of the class hasn't either, okay? So you're doing a service to everybody. Okay? Questions about that? Okay. So that was the first point. The second part of the result says, wait a minute, so I can tell you more than v dot is negative semi-definite. I can tell you v dot is negative definite. In other words, v dot is 0 at 0 and strictly negative everywhere else, right? Now, that information you can use to actually show that this equilibrium point x equals 0 is asymptotically stable. Namely, there exists some ball of radius r0 such that whenever you start in this ball, you get back to 0. You actually do something. So, well, let's pick r to be r0, the biggest we can pick. Okay, so we fix it. The r0 corresponding to where these hypotheses are true. All right. So we can, based on this r0, compute the corresponding best, or at least a corresponding small r0, such that whatever trajectory starts in the ball small r0 will never get out of the ball of radius r0, which is where we've defined all of this. Okay, and perhaps where our model is true and all these things. All right. So we have r0, we can explicitly compute, perhaps numerically, but explicitly compute r0. Okay. And now the question is, how can we use this fact that v dot is negative definite, not just negative or 0? All right. So let's pick a trajectory. Let's pick a trajectory that starts in this ball of radius r0. Okay, and it does things. And we're trying to show that whenever we start in this ball of radius r0, we actually get back to 0. Okay? So let's initialize a trajectory in here, in this ball r0, and we let it run. Okay? So what do we know about v when we do this? Okay, we initialize trajectory somewhere, and we look at v of x as a function of time. Okay? What do we know about it? Yeah, it keeps decreasing, right? So if we look at this particular trajectory, okay, and at v of x, then it's going to do something like this, right? So that's v of x. For this particular trajectory. Okay? Now we also know that, of course, v of x is positive definite, so in particular, a particular consequence of that is, of course, v is positive. All right? So if we have 0 here, we know that v keeps decreasing, and it's lower bounded by 0. All right? So basic result in analysis, you have a decreasing function which is lower bounded. It tends towards a limit. All right? So let's call this limit capital L. And so this, we know that this v tends towards this limit. Okay? All right, so where are we? We've initialized an arbitrary trajectory in this ball small r0 constructed from the big r0. Okay? We followed v of x as a function of time, because x is a function of time for this trajectory. And we know that v of x tends towards a limit, which is positive or 0. Okay? Now, what are we trying to show in terms of this limit if we want to show this theorem? Well, we're trying to show it is 0, right? If we've picked this arbitrary trajectory starting in the ball small r0, we've shown v of x tends towards a limit. If that limit is 0, then we're done, right? Because 0 is the only place where v can be 0, right? V is positive definite. Right? So if we show that this limit tends to 0, we're done. See, if this limit tends to 0, this limit is 0. If we show that L is 0, we're done. Okay? So let's just show this. Okay? And one way to show this is by contradiction. Let's assume it isn't. Okay? So we want to show L equals 0. Well, assume L is positive, okay? Prove by contradiction. Okay? Assume it's not 0, then it's strictly positive, of course. All right? So it means that v of x tends towards a limit, which is always strictly positive. So v of x during all time from 0 to infinity stays larger than the strictly positive limit. Let's say 0.2, okay? All right? So what does this imply about this plot? Okay? Can I draw something on this plot which makes it more precise? I assume that L is strictly positive, and I want to show it leads to a contradiction. It leads to a nonsense, okay? So I assume L is strictly positive. So V will remain larger than this positive quantity L, okay? So what does it mean in terms of this drawing? It means there's a no-fly zone, right? It means there's a region in the state space around 0 that the trajectory never enters, right? Because V is 0 at 0, and it varies continuously. So if V is always larger than 0.2, there's a region that the trajectory never enters. Okay, so if we assume that L is positive, it would mean there's a region around the equilibrium that the trajectory never enters. Okay? Now, why is this a contradiction? Why this cannot be the case? Don't worry, this is kind of the most mathematical we'll do in this course, but these are so simple in some sense, you know, that it's really worth doing once, okay? Right, so don't forget now the new assumption is V dot is negative definite, okay? So in other words, V dot is not only negative, but it's 0 at 0 and strictly negative everywhere else. All right? So what does it mean, and you have this, you know, explicitly in the book, what does it mean that you have this no-fly zone, right? What does it mean that you don't enter this red region? It means that V dot remains less than some strictly negative number, right? Because V dot is negative definite, right? So never enters this, okay? So there exists V dot remains less than some, let's say, minus alpha, which is negative, okay? V dot remains less than some negative number. Okay, so now we have V. We started with a value, 25. And we've just shown that V dot remains less than minus 5 per second. Is it possible that there's a no-fly zone? Well, no, because if it's, you know, if you start with V equal 25 and you have a velocity of, let's say, at minimum minus 5, it will take 5 seconds to get to 0 at most. Okay? This says you have a finite velocity going to 0, whatever happens. So you will cross this red ball. Okay? Hence the contradiction. All right? So you start with an arbitrary trajectory. You notice that it tends towards a limit. You wonder whether this limit can be not 0. If the limit is 0, you're done. If the limit is not 0, it has to be positive. If it's positive, it means there's a no-fly zone. There's a region around the equilibrium where you cannot get in. But if there is a region around the equilibrium where the trajectory cannot get in, it means the velocity will remain less than some negative number, and therefore it will eventually get in. Okay? And so this means you have a contradiction, and therefore you've proved the theorem. Okay. So that's the basic proof of Lyapunov's main theorem. Okay? And you notice that in the context of the proof also you generate explicit r's as a function of a big R, right? And an explicit R0 as a function, of course, of the original R0. Okay, so it tells you the explicit region where this is all true. Okay? Questions about that? Okay. So, questions? All right. So this was the result for the local theorem. So let me state the result for the global theorem. Lyapunov's theorem on global stability. So remember, in the case of global stability, what's the difference in the definition of global stability? It's just that R0 is infinity. Okay, so in other words, starting from anywhere, you tend to 0. Okay? So the question is, well, first of all, what's the theorem? Okay? So it would be natural to say, well, maybe the theorem is just, well, we replace R0 by infinity, you know, assume everything is, you know, infinity and the theorem works. Okay? So it's not exactly true, but almost. Okay? So the theorem on Lyapunov scalar, the theorem on Lyapunov stability in the global sense says the following. Okay? So everywhere, so for all x, right? For, you know, everywhere, meaning in Rn, right? Everywhere, you have so you have found a function v of x, right, which is positive definite everywhere, such that v dot of x is negative definite, right? We don't have to do again the stability part, right? Because the stability is a local question. So we've taken, if we assume this is true everywhere, in particular it's true in a local region, okay? We just have to do the asymptotic stability part. So we would like to show that this implies that this equilibrium point is globally asymptotically stable, which incidentally, as we said, implies there's only one equilibrium point, and therefore we can say the system is globally asymptotically stable. Actually, we need an extra condition, and there's a variety of extra conditions we could add. The simplest one is to add the extra condition that d of x tends to infinity as the norm of x tends to infinity. In other words, as x tends to infinity in any direction. And then this gives you this is a correct result, okay? So this gives you the result for global asymptotic stability, namely, if you can find a scalar function v of x, such v of x is positive definite everywhere, v dot of x is negative definite everywhere, and this orange condition is verified, x tends to infinity as v of x tends to infinity as norm of x tends to infinity, then the equilibrium point, and therefore in this case the system, is globally asymptotically stable. Okay. So this extra condition, which we added, is called radial unboundedness condition. And let me explain why you need it. Well, it's just basically because as you start going from finite results to infinity, right, as soon as you start playing with infinity, you know that you have to be a little careful, you know, that's from integrals and things like that, okay? So here is the same story. Okay. So what is this condition trying to avoid? Well, think of, you have, let's say you have the plane which represents the state space, let's say a two-dimensional state space, right? V of x would be some kind of shape in the state space, which is 0 at 0, okay? Some kind of ball-like thing. Okay. And we can think about the contour lines of V, which are, you know, basically just like in the mountains, right? They correspond to, these are the value of x corresponding to a particular value of V. You know, V equal 125, you have something, and V equal 78, you have something else, and so on. Okay, so you have the contour lines. So let's pick it in the two-dimensional plane. Okay, so suppose we have x1, x2. Okay. So what we're trying to avoid is that the contour lines look like this. Okay, so for instance, you know, this would be just picking some simple numbers, v equal 1. And then v equal 2 is something like this, and v equal 3 is something like this. So this is v equal 3, v equal 2, v equal 2, v equal 3. Okay. So what's going on here? That's what we're trying to avoid, okay? What's going on here is that if we pick a particular trajectory, it's very possible that it keeps going towards smaller and smaller values of v. So v keeps decreasing, but you actually drift away to infinity. Right? We're trying to avoid this. That as v decreases, well, it does decrease, but in decreasing, because we're playing now with infinity, it actually drifts away. Right? So what is this condition doing? Think again of this plane and the v shape, the v function, right, as a function of this plane. This condition is kind of pulling v up at infinity, okay? It's pulling it up, it's lifting it up. So you see, if you lift it up, basically you're going to create closed contour lines, and this will not happen. Okay? So that's what this condition is about. It's basically about trying to create closed contour lines, making sure that when you tend to infinity, you cannot have v equal 2. V has to tend to infinity. Okay, so now, so how do we prove this? Well, that becomes very simple, because it says if this condition is true, the orange condition is true, okay, then we stay in a bounded region, okay, because basically all the contour, you know, or v tends to infinity as x tends to infinity, the contour lines are closed. So if we start somewhere, we're going to stay with v less than something, and that will define a bounded region. Okay? Imagine again this shape. You'd say v less than something and describe a bounded region. Okay? And so then, because it defines a bounded region, you can play again the game of the game of velocities that we played before. Say it tends towards a limit. Can this limit be not 0? Okay, and show that indeed it does tend to 0. Okay, so that's the result for global asymptotic stability. So let's look at some simple examples. So the kind of quasi-trivial example, so scalar system, x dot plus c of x equals 0, and we assume that C is continuous and x, C of x, is strictly positive for non-zero x, which means that, in English, it means that C is the same sign as x, right? Okay, so we have x, and we have C of x, and notice I've made C go through 0. C of 0 is 0. Okay, and it's 0 only at 0. It's not an extra assumption. It's a consequence of the fact that, you know, C is positive for x positive and C is negative for x negative, and C is continuous. Okay, so it has to look like this. All right? Everybody understands this, right? So I have a function which is continuous. All this is scalar, right? It has the same sign as its argument. So it looks like this. And it has to go through 0. Okay? So, now, what's an equilibrium point of this? Of this system? First order scalar system, right? So this is not a very profound, right? It's just 0, right? Because C of 0 is 0, as we said. So this equilibrium x equals 0. So the result is that this equilibrium s equals 0 is globally asymptotically stable. Okay? So how can we show this? Well, we're trying to use this result, right? So we need to come up with a scalar function z of x. And such that it works. Okay. Any candidates? So that's the first example is both trivial but useful, but also it shows, you know, the flavor of using these Lyapunov results is that there's nothing in the Lyapunov results, and to improve that you have to take very good classes, right? There's nothing in the Lyapunov results which tells you what is V. How should you pick V, right? So what's a choice of V? Yeah, so here, you know, so the proof, right? Suppose we choose V equal x squared, right? Right, so what can we say about this x squared, right? Well, it's clearly positive definite, right? Positive, strictly positive everywhere except at 0 where it's 0. It clearly also tends to infinity as x tends to infinity. What about v dot? Well, v dot is 2x x dot, which is minus 2x c of x, which is strictly negative unless x equals 0. Right, v dot is 2x x dot minus 2x c of x. So that's strictly negative unless x is 0. In other words, v dot is negative definite. Okay? So we have these 3 points. V positive definite, v dot negative definite, v tends to infinity as x tends to infinity. And so this equilibrium x equals 0 is globally asymptotically stable. All right? Which means starting from anywhere, the system tends towards 0. So for instance, if we take x dot equal minus x cubed, this system is globally asymptotically stable. So starting anywhere, you tend to 0. Okay, starting at x equal 174, you tend to 0. Okay? You can play games with it. So for instance, suppose we do this, right? X dot plus x equals sine square x. So, you know, hand-wavingly, it's not quite obvious what happens, right? Because you have this kind of first-order filter and then this positive quantity. But well, the system is also globally asymptotically stable, right? So how do we show this? Well, we want to show that the corresponding C of x, right, has the right sign. And in doing so, the easiest way is something we'll do very often, is to start with something which obviously has the right sign, and to show that the other term is smaller than it in absolute value, right? So of course, if we had x dot plus x equals 0, that would work, right? With C of x would be x, right? So to show that C of x is the right sign, we just want to show that sine square x is less than x in absolute value unless x equals 0. Okay? And of course, that's true because sine square x is less than sine x. Why is that? Because sine is less than 1, right? And sine x is less than x unless x equals 0, because, of course, if you plot the sine function, then you take the tangent at 0, right, and you have x. So sine x in absolute value is less than x in absolute value. Okay. So x has the correct sign, and you're adding to it something which is smaller in absolute value, so the sign remains the same. Okay? Is that fine? So this is globally asymptotically stable, and this the equilibrium point x equals 0 is also globally asymptotically stable. Okay? Questions about this?
Does V always has to go to infinity?
It's an extra condition. You could have other, but more technical.
It could be like, doesn't have to go to infinity.
No, you could also say well, you could say the contour lines are closed and things like that. You know. And also, you could prove directly that indeed things work. So it's always a sufficient conditions. Okay, so questions about this? Suppose we just looked at this example and looked at the linearized version of this. What is the linearization of this example? It's x dot equals 0, right? So the linearization is marginally stable, but the real system is globally asymptotically stable. Right? So this is why, you know, we put a question mark in the Lyapunov result on linearized systems when we said if the system is the linearization is marginally stable, then who knows, right? We put this question mark. And the reason, for instance, you can see it here. The system is perfectly fine. It's globally asymptotically stable. We start it anywhere, it goes to 0, right? But the linearization doesn't tell you that. And again, the linearization doesn't tell you that because it's the same linearization as if we had x dot equal plus x cubed, which obviously would not be stable. Okay? So this shows you in this proof also you have to come up with your Lyapunov function candidate, okay? You can see that, of course, it's not unique, right? So what could be another candidate here? Well, obviously, we could choose 2x squared, right? It would work as well, right? But we could also use x to the 4th. Or we could use 2x squared plus x to the 4th, right? These will all work as Lyapunov functions. we could do perhaps something a little more subtle. We could use integral over from 0 to x of c of y dy. Right? Because this would give us v dot equal what? Well, c of x times x dot, in other words, minus c square of x, right? So this would again work, right, as a Lyapunov function, except you would still, you have to assume that it tends to infinity as x to infinity. In other words, that c of y doesn't tend to 0 too fast. So that would be an extra assumption. Right? But you see, you could, nobody tells you, at least this theorem doesn't tell you how to find the Lyapunov function. And of course, the Lyapunov function is not unique. Okay. Okay. Questions about that? All right. Any questions? Now, so that was, you know, the status of things up to the 1960s. And we'll see more examples based, of course, on these Lyapunov theorems. But one of the difficulty of these Lyapunov theorems, of using these Lyapunov theorems, was something which we have played with earlier. Remember, we had a mass spring damper system. I won't redo the whole thing, right? But we had a nonlinear mass spring damper system. And we created for it a function z of x, which was positive definite, which was the total energy. And when we computed the derivative of that energy, we found the power dissipation, which in this case was of this form. So this was all good, right? Except, of course, the power dissipation is not negative definite. It's only negative semi-definite, right? Because v dot is 0 when the velocity is 0. Okay? Basically, you have this nonlinear mass spring damper thing, which tends to 0. But v dot is 0 whenever the velocity is 0. Okay? Which means actually whenever it changes direction or it has stopped. Right? Same thing if you were playing with a pendulum here, you would take the total energy and you would find that v dot is 0 whenever it changes directions. All right? So in other words, if you're trying to show the global asymptotic stability of this system, actually you cannot quite use the Lyapunov theorem we stated as such, because basically you'll be able only to use the local version. Okay, you'll be able to, you'll be able to only use the fact that it's stable, only to show that it's stable, but not that it's asymptotically stable. So you could say, well, you know, you can come up perhaps with slightly different Lyapunov functions, not energy plus something, which fixes that, and you can. Okay. But on the other hand, it would be nice to be able to kind of follow the original physical reasoning and be able to conclude when v dot is only negative or 0, but not necessarily negative definite. Okay? And so that led to the development of a new class of theorems, which are still, called Lyapunov theorems, but were derived by Lassalle in the 60s. And they are called the invariant set theorems. So what's the idea of the invariant set theorem is to say, well, let's keep right with the reasoning of Lyapunov. We have this total energy, and this energy keeps decreasing, and so on, okay? So there's this technical point that power stops being dissipated, not just here, but whenever we change directions, right? And basically the idea of Lassalle's theorem is to say, okay, fine. This is kind of technicality in a sense, right? Because we arrive here, we change direction, we keep going. So if we can show that basically we don't get stuck when we change direction, we should be fine. All right, so that's the intuition. It says, okay, the power dissipation is strictly negative, unless, of course, we are at rest, but also whenever we change directions. Let's push aside this case where we change directions by saying we're not staying there anyway. The system keeps going. Okay, this is not its final behavior. It doesn't do that and stop. Okay. But of course, just as Lyapunov had done, this was formalized in a much more general mathematical argument. Okay, and so that's what we want to talk about now. So it's based on the notion of an invariant set for the dynamics x dot equal f of x. So this invariant set, so what's an invariant set? Is a set such it's a subset of Rn, right? It's a subset of the space, okay? Such that if you initialize the system somewhere in this subset, the system can move, of course, but it stays there. It stays in the subset. Right? So you have some region of the state space. And whenever you start in that region, you stay in that region. So, for instance, what do we know? What kind of invariant sets do we know? Well, the set corresponding to an equilibrium is an invariant set, right? It's a point, right? If we start there, we stay there. There's some more trivial things, like, of course, the whole state space is an invariant set, hopefully. Or at least if your model is reasonable, right? So, but that's not really useful, but showing that you tend towards, for instance, if you have a result, say, I tend towards an invariant set, well, it could be the whole state space, so by itself is not really interesting, right? Something a little more subtle, we have these autonomous systems, right? Suppose you initialize it somewhere, it follows a trajectory. And so this trajectory, it covers a path in space, okay? Difference between the path and trajectory is, a trajectory is a path as a function of time, okay? So it covers a path in space, right? Well, any such path is an invariant set, right? Because if you initialize it along this path, it will follow the corresponding trajectory, right? So so let me put it in quote, trajectory, by which I really mean the path followed, right? That's clear, right? You start somewhere, it's an autonomous system, so you follow a trajectory, you cover some place, right? If you started somewhere else on this trajectory, you would still cover it, and you stay there, of course. Now, something which can be quite practical too and which was the second motivation for this invariant set theorem. The first motivation was to get rid of this technicality where you know the system has to tend to zero from physical reasons, but you're stuck with this, where you have this condition that v dot needs to be negative definite, which is a little too strong. Okay? So that was one motivation. The other motivation of this invariant set theorem was to say, well, you know, it would be nice also now that we are in this nonlinear world, not to be limiting ourselves to convergence to equilibrium points. You know, lots of things could happen. We could converge, you know, to strange attractors or whatever. We could converge to limit cycles, right? The limit cycle, you know, perhaps corresponds to a set where you keep doing the same thing, right? In the state space, so you keep following some curve in the state space, right? If that's what the system does, you know, it would be nice to be able to show this, right? But you, starting from anywhere, you end up with this behavior where you keep doing the same thing in some region. Okay. So, two main motivations. Replacing the negative definiteness of v dot by something a little looser, and being able to study convergence to more general systems, to more general behaviors. Okay. So it turns out, so the statement of the theorem is a little looser than the statement of Lyapunov's main theorems. And its conclusions are a little looser too, right? It's not that it's a better theorem, it's the hypotheses are a little more general and the conclusions are a little less precise. Okay. But that's what's available. Okay. So we'll start first with the global case. So, so again, of course, x dot equal f of x, right? We don't assume anything about equilibria because this will come in the theorem itself. We don't assume anymore that v is positive definite or so. We have looser assumptions. And that's the result. Okay? So we still want a scalar function v of x, which has two properties. V dot of x, we can still talk about v dot of x, right? Because we're still with autonomous system, is negative or zero everywhere. So if you want, it's. But we don't say what its value as 0 is anyway, so it's just negative or 0 everywhere. And we do add this radial unboundedness condition. That v tends to infinity as the state tends to infinity in any direction. So that's the hypothesis, okay. Then all trajectories tend toward the set R defined by v dot of x equals 0. Right? Remember, v dot is a function of x only, so v dot of x equals 0 defines a subset. And all trajectories tend towards this subset. Okay. That, as you can imagine, is not very hard to show. The more technical point, so we won't give the proof of this full theorem here. It's discussed in the book. More precisely, not only you tend towards the set R, but more precisely, all trajectory tends toward the largest invariant set within R. Okay, so that's what the theorem says. What does this mean? So, by the way, the subtlety, the subtle part of proving this theorem is to show that indeed there's an invariant set within R. Okay? It says the largest invariant set, which assumes there is one. That's the theorem says as well, there is one. So, first of all, what does it mean largest? It has nothing to do with size. It just means the reunion of all invariant sets. Okay, so some trajectories tend towards some invariant set, and some other trajectories tend towards some other invariant set. And so all trajectory tends towards the invariant set, which is just the reunion of all the invariant sets. Okay, so some may tend towards equilibrium, some may tend towards limit cycle, whatever. Okay, so that's what it means. Okay. Now, so it sounds a little technical, but as we'll see, very often it's quite easy to apply. And so that's what we're going to do right now. So let's look at an example. Let's look at the system x double dot plus b of x dot plus c of x equals 0. X is scalar, right? Where c has the same sign of its argument, namely x. B has the same sign as its argument, x dot. Okay, so I won't redo the big drawing I did before, right? I just so it means that B and C are continuous, of course. So C of x could be again something like this, which has to go through 0. And B of x dot could be something similar, which also has to go through 0. Okay, so they are both continuous and have the same sign of their argument. Which implies that they go through 0. Then, within a small extra assumption, which we'll show, okay, x equals 0 is a globally asymptotically stable equilibrium point. All right? So fairly general theorem, right? Second order system. B of x dot, same sign of its argument as its argument. C of x, same sign as its argument. this implies, first of all, that 0 is an equilibrium point, but that's obvious because we say they have to go for 0. And 2, the theorem says, or the example says, what we're going to show says, this equilibrium point x equals 0, and of course x dot equals 0, right, is globally asymptotically stable equilibrium point. Okay? So how do we show this? Hint, of course, we show this after stating this, which was meant to say, well, we're going to try to fix the small problem with Lyapunov basic theorems. How do we show this? Well, using this notion that Lyapunov basically introduced and which became very useful later on when people started working in robotics, which is the notion of virtual physics, okay? This question, this system, x double dot plus b of x dot plus c of x, could come from economics, could come, from, study of development somewhere far, okay? It could be it could come from anywhere, but it could also very well come from a freshman course in the mechanical engineering department, or actually, for that matter, a basic physics course in 11th grade. Okay? And so, if it did come from a course in mechanical engineering, most likely it would be describing what? Or mass spring damper system. Right? This is a spring term, right? It's something which depends on position and pulls you back. It has the same sign as this argument. Okay? And this is a damping system. It's something that opposes velocity. Okay? And again, where these equations really come from could be something completely different, right? But these are the same equations you would have if it was a mass spring damper system, okay? Or if we move a few buildings away, an RLC circuit, okay? And with an RLC circuit, you could have nonlinear inductances, so you could have a little more fun, okay? But here the system has mass 1. Okay? So if we see it this way, of course, it's fairly obvious where we should pick our Lyapunov function candidate or our LaSalle function candidate, okay, our candidate for the invariant set theorem. What should it be? Well, reasonable place should be the total energy of the system, right? So remember, we call this the state X, right? So what's the total energy of a system? If it was a mechanical system, right? It may, again, come from something completely different. But what's the total energy of a system? Well, it's kinetic energy, so the mass is 1, okay? So 1/2 of x squared, x dot squared. And then the potential energy of the system, which is? Yeah, so it has to do with the work that the spring would do, right? So it's the integral from 0 to x of c of y dy. Right? So, does it satisfy the assumption? Well, it's scalar, right? Does it tend to infinity as x tend to infinity? Well, actually, you see that's not entirely guaranteed by that. That's where the small extra assumption comes from. Okay? And assume also the integral from 0 to x to plus or minus infinity of c of y dy is infinite. Well, actually, it's plus infinite. It has to be plus infinity. Yes. All right. So this is a very small assumption, right? It's just saying that this spring term either stays at some value, right? Or if it really disappears, it disappears slowly, right? This is reasonable assumption, right? It just says, at infinity there's still something pulling you back, right? That's all. Okay, so that's why you have this extra assumption. Okay, but of course, for instance, if you know the spring term is lower bounded by 1, then of course this assumption is always verified, right? Okay, so everybody understands why we have a small extra assumption. That's really not a big deal. It's very natural, right? Okay, so how do we show this? Well, we can do it both ways, the long way and the lazy way. Okay, so let's do it the long way because we haven't not yet lazy enough. Okay. So the long way is to just differentiate all of this, right? And we should remind you of a calculation we did before, of course, with the mass spring damper system. So what's the derivative of this? X dot x double dot. What's the derivative of this? Right, C of x dot. So x double dot, of course, is minus b of x dot minus c of x. And then we have this x dot c of x. So the usual miracle happens, which again, is a engineered miracle, which comes from our definition of potential energy. Which is, of course, that this term cancels this term, and you end up with minus x dot b of x dot. Okay? And again, if you had done it the lazy way, you'd have said, well, this could be the total energy of a mass spring damper system if this was a mass spring damper system of mass 1. So its derivative would be the power dissipated. The only thing that dissipates power is the damper. So you could directly write it as x dot b of x. Right? So I'm saying virtual physics because they may not be a real mass spring damper. So this would be a virtual total energy, and this would be the virtual power dissipation. Okay. So here we are. And of course, this x dot minus b of x dot is negative or 0. Okay, it's always the same thing. It's the same thing as this, right? It's basically you stop dissipating energy whenever you change directions. All right? So how do we finish this? Well, we want to use this result. Okay? So the first part of this result will tell us that we tend towards the set where v dot equals 0. Okay? So in other words, using the invariant set theorem shows x dot tends to 0, right? Because it's the only place where v dot is 0. So it means we stop. That's the set R. Just corresponds to x dot equals 0. Now the theorem is more precise. It says not only we tend towards R, but we tend towards the largest invariant set within R. Okay? So very often in using this theorem is the within R, which is what helps you finish conclude the result. Okay? We tend towards an invariant set within R. So in particular, we stay in R. Right? So it says, suppose we start in R, so suppose x dot equals 0. Do we stay in R? Well, what do we compute? We compute x double dot, right? Whether x dot remains 0. Right? If for x dot equals 0, we have some non-zero x double dot, then we might not stay in R. Okay? So what's x double dot when x dot equals 0? Well, we use the dynamics, first line up there, right? X dot equals 0, so b of x dot is 0. So we just have minus c of x. Right? Not surprising, right? When the system has stopped, the only force pulling on it is the spring. Right? When the system doesn't move, there's no damping. Okay? So everybody understands that just algebraically, right? When x dot equals 0, you plug it up there. You know that b of x dot is 0 at 0, red curve, right? And you just get minus c of x. Right? Now, of course, this cannot be 0 unless c of x is 0. Right? Because of the yellow curve up there. Okay? So the only way you tend towards an invariant set within R is if x dot equals 0, of course, you're in R, but also if c of x equals 0. And the only place where c of x is 0 is x equals 0. So system is globally asymptotically convergent to x equals 0, x dot equals 0. Okay. So we used this theorem, but when using the second part, what was the key to make it simple was to say this condition that we stay within R tells us actually all the information. Okay. So we have this system. We can imagine it's a mass spring damped system even if it isn't. If we do so, it gives us a hint of what should be a good Lyapunov function candidate. We find, not surprisingly, that it works, but we have this problem that v dot is not negative definite, so it's only negative semi-definite. But we can fix this using the invariant set theorem, which says basically v dot will be 0 whenever you change directions, but you never get stuck here. If x dot equals 0, x double dot isn't. Okay? Okay. So, for instance, if you take the system x double dot plus x dot cube plus x5 is equal to x4 sine square x, right? So this system is globally asymptotically stable. In other words, starting with x equal 1024 and x dot equal 365, right? It will come to x equals 0, x dot equals 0. Okay. Why again? Because of course b has the right sign, right? And this has the right sign. And this you can easily show is less than this in absolute value. Okay. Now, as a last remark, so we'll make two remarks next time about, simple applications of this to control. Okay. So the first, which we'll expand on, is the fact that because you're dealing with inequalities everywhere, things have to be positive, things have to be negative, and so on, it's a very natural way to deal with robustness questions. You know, what if I know I don't know a parameter exactly, but I know only a certain range? Okay, because you deal with inequalities all the time. Okay. Second point, which I'll make briefly now. Suppose you have a system like this. X double dot plus x dot absolute value of x is equal to, let's say, x squared. X dot absolute value of x dot is equal to x squared u, right? So u now is a control input. Can somebody give me a control law measuring whatever you want? Can somebody give me a control law that makes the closed loop system globally asymptotically stable?
U equals minus A.
Right. So if you use u equal minus x, right, the closed loop dynamics will be x double dot plus x dot absolute value of x dot plus x cube equals 0. And of course, it globally tends towards x equals 0, x dot equals 0. Right? Now, the funny thing here is actually this is a linear controller, right? U equal minus x. And it does make this nonlinear system go to 0 globally, starting anywhere, any initial position, any initial velocity. But suppose you had started from a linear analysis, which you know would only be local, but at least try, right? What's the linearization of this system around x equals 0, u equals 0? Well, the linearization is x double dot equals 0, right? Or as we wrote it, x double dot equals 0, right? The linearization of this is 0, and the linearization of that is 0. Okay, around x equals 0, u equals 0. So here, the linearization is not a control problem, right? The linearization is x double dot equals 0. There's no control input in the linearization. While, of course, the real system has a control input and actually can be controlled by a linear controller. And be controlled nicely, right, globally. Right? But you see that when you throw away the baby with bathwater, you might also throw away the control input. Okay? So next time we'll talk about how can these tools can start being used to look at robustness. Very simple example. We'll do much more in the rest of the course. And also how they can be used to show convergence to different behaviors like limit cycles.